This is the section 2.4 pre-class notes. We're going to be defining complex numbers. Define standard form of a complex number, which is written a plus pi. You can see that right there. Perform operations with complex numbers, and then simplify powers of I. So we do need a little background knowledge here. I'll show you kind of with this box down here. It says the solution to x squared equals 9 is 3 or negative 3. Those are both considered to be integers. If you wanted to take the square root of 9/4, you'd have a 3/2 and a negative 3/2, which are rational or ratio numbers. If you wanted to take a square root of 5, you would get something that's not nice. It's a non-terminating, non-repeating decimal, and those are irrational. Up to this point, we've never been able to solve x squared equals negative 9 because that would make, when you go to take a square root, you would get a negative under your radical. And in real numbers, that doesn't exist. So we now have a new number that we're going to talk about and define. So when you're a little kid, you learn about the natural numbers. And this was on section 1.1 notes that I handed out. Those are things like 1, 2, 3, on and on and on. When we add in 0 to that group, we now are talking about what we call the whole numbers. If you add in negatives or opposites to that group, and this keeps going, you have the integers. If you add in terminating decimals, repeating decimals, so something like 0.7 repeating, and just regular old fractions, that's when you have your rationals. Things like pi and square root of 3 that don't reduce down nicely, or they have a decimal that goes on forever with no pattern, are called irrationals. And those two groups, the whole tree down below, all make up the real number line. Adding one extra guy is going to change everything. A square root under a negative under a square root, we use -1 just to emphasize just a generic negative, is now going to help us do a whole new group of numbers called the complex. We don't like writing that negative under the radical, so we use the symbol I to represent the square root of -1. And by doing that, it cleans up a lot of our problems and lets us work with those algebraically. So the complex numbers has everything that we had normally plus this new element. Now, some important things you have to have memorized. It's just some definitions. These two properties are things that you have to know. Anytime you see a negative under a square root, it will be pulled out as an I. You pull out the I as kind of our joke. And then I squared is just squaring both sides, so I squared has to equal -1. And that, anytime you see I squared, you must change it to a -1. Okay, here's just some summary of different things. Complex numbers written in standard form are a plus bi, where a is a real number and b is an imaginary part. If you have just the b part without the a part, that would be what we call a pure imaginary number. If you just have the a part without any i's, you would be a pure real number. And then these are rules for adding and subtracting, but they actually make things look more complex. The way I think of adding and subtracting is just adding and subtracting like terms, because that's essentially all it is. So I would distribute this negative because that's a subtraction sign. So that's -2 and -3i. Combine like terms, so -3 and -2 is -5. 8 minus 3 is +5i. And this is written in a plus bi format. So that is the end of that one. Something like this we would FOIL like normal, so 56, 8 times -3 is -24i, 2i times 7 is +14i, and 2i times -3i, be careful here, 2 times 3 is -6, I times I is I squared, but remember I squared is always -1, and it actually goes away once you've replaced it. So this is actually 56, I'm going to go ahead and combine like terms in the middle. That would be -10i, and this is -6 times -1. That's actually +6. So an I squared attached to a number will turn into the number into the opposite sign with no I. So then 56 and 6 would be 62 minus 10i. This one's being squared. Remember, there's a plus here, so that means you have to write it twice and FOIL. So 6 times 6 is 36. 6 times 7i would be 42i. 7i times 6 would be another 42i. And 7i times 7i is positive 49i squared, but I squared is negative 1, so that actually makes this overall thing a negative 49. So 36 minus 49 would be negative 13, and then plus 42 would be 84i. So essentially, adding, subtracting, and multiplying with imaginary numbers are fine as long as you know the rule about the I squared. Okay, our last topic on 2.4, because this is one I like to spend more time on in class anyways, is powers of I. We already know that I to the first is just I. Making a little diagram here. I squared, we learned, is negative 1. I cubed is an I squared times an I to the first. That means it's a negative 1 times an I, or just negative I. I to the fourth is 2I squared, so I squared times I squared, which is negative 1 times negative 1, or positive 1. Now the cool thing is, when you get back to I to the fifth, it ends up being the same thing as I to the first. Let me show you that. I to the fifth is I squared, another I squared to make 4, and an I to the first. This is negative 1 times negative 1 times I. Negative times negative is positive, so it's just I. So if you did I to the sixth, it would be negative 1. I to the seventh is negative I to the eighth is positive 1. It just cycles over and over again. Now, if you had a small thing like I to the 13th power, you could just count. You could just say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. It would be I. We're not going to be giving you tiny numbers, though. Like if you look at our example below, we give you 66. You're not going to count around 66 times. Well, you could, but I wouldn't recommend it. So we have a different rule that we use. Since this pattern is repeating every fourth round of the circle, if we just divide the exponent by 4, we should be able to figure out how many times it laps around and where does it end up. So 4 into 6 is 1 time. Subtract and you get 2. Bring down the 6. 4 into 26 goes 6 times, which would be 24. And subtract that and you get 2. The key to finishing this problem is the remainder. This thing makes 6 complete laps around my little circle up here with 2 left over. So that means it ends up at I squared, which means it is negative 1. So whatever the remainder is, that's the power it reduces down to. I'm going to go to 92 first because the middle one has the negative exponent. So 4 into 9 goes 2 times. That's 8. That's 1. That's 12. 4 goes into 12 3 times with a 0 remainder. So essentially this guy is like I to the 0, but that really just means you're I to the fourth. So I to the fourth, or I to the 0, anything to the 0 power is positive 1. All right, now let's talk about that one in the middle that has the negative exponent. You cannot do powers of I with a negative exponent. You have to have it in positive exponent form. So we're going to move that first. So that would be 1 over I to the 55th. Then I'll go ahead and do my division. 4 goes into 55 1 time. Remainder is 1. Bring down the 5. 4 goes into 15 3 times. 12. Bring down and get a remainder of 3. So that means that this is going to reduce to 1 over I cubed because of the remainder of 3. And I cubed, we look up our chart, is negative I. Now the problem with this is you're not allowed to have I in a denominator because I is really a radical of negative 1. So we have to get rid of it. The way to get rid of an I in the bottom, if it's just by itself with no binomial attached to it, you just multiply top and bottom by I. So this is I over negative I squared, and I squared is negative 1. So that would be I over negative negative 1, which is just positive 1 on the bottom. So the final answer is just I. Okay, that concludes our notes for that section for the pre-class notes.